So hello everyone, my name is Abhishek, MTech first year. Today we will understand the problem given in the assignment. Here is the problem. So we have to simulate the two degree of freedom system in the Matlab. So we have the x1 and x2 at the displacement of the first and the second mass, and we are taking the x1 dot and x2 dot at the velocity of the first and the second mass. K1 and K2 are the spring constant for the first and the second mass, where one of the spring is the linear and one of the spring is the non-linear. K1 is the non-linear spring and K2 is the linear spring. The first mass is excited by the A sin omega t, and the second mass is excited by the white noise. So we have first written the states equation of the motion, and then we have written the state space formulation y1 is equal to x1, y2 is equal to x2, y3 is equal to x1 dot, and so on. So we have find the drift matrix A is equal to like that A dt plus V W, and the dispersion matrix like that. Now we'll move to the code. So here is our code. So here t is equal to 100 means total time is equal to 100 and dt is equal to zero point 0.1. So for each step it is taking at the value zero point 0.1. Say symbolic td, it's making the function expression for the td which is in symbolic form. So which we will use in the expressions. T is equal to 0 dt t minus dt. It is calculating from 0 to each time step zero point 0.1 up to 100 minus zero point 0.1. Now nt is equal to length of t. It's making the matrix which is the length which is making the length of t. It is not making matrix. It is showing the nt is equal to length t means up to the value which are going in the t. Delta matrix what square of root of dt 0 delta t raised to power 1.5 divided by 2 here that matrix we which use in the Taylor 1.5 series. Here the delta w delta z matrix where h is equal to delta t which is the time steps, and u1 and u2 are the random variables. So next we have the y is equal to 0 for nt. So y is equal to 0 for nt means 4 here denotes the row. So y1 y2 y3 y4, and nt denotes the columns. So columns are the is equal to length of t for each value of calculated t. Now y comma a comma b is equal to s of duffing. Here the function which we will define later in the last. Here another function Taylor L0 L1 we will define later. Now av is equal to Matlab function a y comma td. It's converting symbolic expressions of a into the numerical value by taking the value of y and td. So similarly for the L not AV and the another one. Now we are moving towards the loop. Here TD is equal to 0. It is not the initial value is equal to 0. Now for the another one, I is equal to 1 to nt minus 1. It is moving towards the loop here from 1 to nt minus 1. And dw1 and dz1. Here dw1 is the one is the first row of the delta matrix, and dz1 is the second row of the delta matrix into random variable 2 comma 1. We have defined here u1 and u2 are the random variables, so it is making the 2 cross 1 matrix, 2 cross 1 matrix. So it is multiplying with that random variables. Now here L naught A is equal to L naught AV YTD. We have defined that L naught AV, L naught A will L naught AV is the numerical value which we get from the L naught A by giving the value of Y and TD. So we are giving here Y and TD values, and when we are getting the L naught A, L naught B, L1A, etc. Now A coefficient is equal to AV Y comma TD. We have also defined AV, so we are getting numerical value of AV by giving the value of Y and TD. So here similarly for the B coefficient. Now we have the expression for the Y here, which we have studied in the course. That expression is that. I also written here. So that expression is that. So we will solve for that expression. So we have written the coefficients of each terms here. So now TD is equal to TD plus DT. So for the first point one, it will calculate. Then point one plus point one, it will calculate. Now it will move in the loop. Now we are plotting the phase portrait. Phase portrait will be displacement versus velocity. On x-axis there will be displacement of the first mass and the velocity of the first mass. Then similarly for the phase portrait of M2. Now we are storing the response here. Y1 comma semicolon 1 denotes the one uh, One denotes the row, first row and all the columns. Velocity one denotes the third row and all the columns. Similarly, for the acceleration one, displacement two, and the velocity two, acceleration two. We have differentiate the velocity to get the acceleration. Similarly, if we upload all the data for the m1 and the m2 displacement and the velocity curves. Now we are moving to the function which we have talked earlier at L0 L1. So here, here L is equal to size a comma 1. What is noting? It is noting a1 denoting the row. So size of the row of the A matrix, which is equal to 4 in our case. LB is equal to size b comma 2. 2 denotes the column. Size of the column of the B matrix, which is in our case is 1. So miscellaneous is equal to symbolic zeroth size A. What is making it? Making the initial a zero matrix of the symbolic expressions of the A. Now MISC2 is equal to del A by del T. What it's doing in many of the cases that is not required, but in our case there is a function A sin omega t. So we have to find in the L naught expression del A by del T. So we have a differentiation of A comma TD A with respect to T. Now MISC is equal to MISC2 plus MISC. What it's doing? It's MISC is going in the loop and it's calculating the value, and again we are putting it in the loop. Now, for j is equal to 1 to LA, MIC is equal to MIC plus AJ, comma, differentiation AYJ. So what it's doing? What it's doing 1 to LA. 1 to LA means LA is equal to 4. We have defined LA 1 to 4. It is going. So A1 del A by del Y1 del A by del Y2 del A by del Y3. Then for K is equal to LB, LB is equals 1, LA is equal to 4, LA is equal to 4. Then it is calculating B11, B21, B31, B41. So it is calculating L naught A. L naught A is equal to A del by del X, here A del by del X plus B by 2 plus, into del square by del X square. But also there is a term del A by del T here because of the sin omega T terms. Now L naught A is equal to MISC here, which we are calculated from here. Now MIC is equal to symbolic for the similarly for the B matrix we have calculated here L naught B, which we have similar way we have calculated for L naught A. Now for L1A I have calculated, for L1A I have calculated, we know L1A is equal to B del by del X. So B into 1 to 4, so it is calculated for B1, B2, B3, B4, as I have the B matrix B1, 2, 3, 4. So similarly it is calculating then for the similarly for the L1B. Now for L1 L1 of B we are calculating for the differentiation of L1B, because we are find to B into del in L1B by del Y. Now we have also defined another function as duffing Wiener. So here degree of freedoms are 2. So state space equal 2 into degree of freedom. So for the y is equal to symbolic y state 1, it is making the converting the symbolic expressions. Now we have s theta x. What is s theta x? S theta x is the used in the amplitude of the white noise, and the omega 1 and omega 2 are the values. So m1 m2 mt1, so we will provide that values and we will simulate our code to get the stable solutions. Now A, which we have defined earlier, so A is that matrix which I have defined earlier. Similarly the B, so we'll now simulate the code. So here I have provided very less value of s theta x, means amplitude of the white noise is very less, and amplitude of the sine omega t is very high, very large. So what is the figure 1 is giving? Figure 1 is giving the phase portrait of M1 and figure 2 is giving the phase portrait of M2. So this is the acceleration of M2, the velocity of M2, displacement of M2, acceleration of M1, velocity of M1, displacement of M1. Now this is the for the mass 2. Mass 2 is excited by the uh, mass 2 is excited by the white noise. So here we are getting not a stable solution. So we can simulate the many values to get the stable solution. Thank you.